Hello, my name's Christopher Harvey-Hawes. I'm a PhD student at the University of Canterbury under the supervision of Professor David Wiltshire. And I'm going to be talking about strong gravitational lensing as a test of cosmological models. So, give you a bit of overview. I'm going to be talking a little bit about the standard model of cosmology and the tensions and kind of motivating this work. And then I'm going to be talking about strong gravitational lensing and a bit of background about what that is. And then finally, my methodology, data results, and conclusions. So, the standard model of cosmology is based upon the cosmological principle that the universe is homogeneous and isotropic on large scales. So locally, we know that the universe isn't homogeneous and isotropic. We have, structures, you have voids and filaments and clusters and such. But on large scales, on large averages, the matter density kind of evens out and it's smooth in all directions. And the ΛCDM model is based upon spatially flat FLRW backgrounds. And so, yeah, and this has been very successful at describing a large number of cosmological phenomena. However, there are tensions, most notably being the Hubble tension. So the value you get for your expansion of the universe varies depending on the measurements you use to infer it. So if you look back at the early universe at the CMB and work out a value of H0, propagate forward, and compare that to values of the expansion from late universe measurements, there is a discrepancy there. That's a 5 sigma tension, depending on how you define it. But there are other tensions. There's the quasar distribution dipole, CMB dipole, anisotropies, primordial lithium abundance, just to name a few. And this is motivated people to look at alternate cosmological models. So these being WCDM, W0 WACDM, or variants of lambda CDM. So these reparameterize dark energy or additional things, and they're very topical right now with the DES results. However, they are still based on a spatially flat lambda CDM model. So I'm going to be talking a little bit about timescape, which is not based on these spatially flat FLRW backgrounds. So the timescape model, well, first of all, it's very convenient to use. It has the same number of free parameters as lambda CDM. So where lambda CDM can be parameterized by your matter density, your omega m naught, timescape can be parameterized by your void fraction, FV naught. Timescape is based on the average evolution of the Einstein equations. So you have these backreaction terms, which account for local inhomogeneities. So the effect of filaments and voids and structure in the universe. And this means that the global average geometry can vary dramatically from your local geometry. So depending on your position observer, your calibration of clocks and rulers will change. So now a bit about strong gravitational lensing. So gravitational lensing is where the light from a distant source, so a quasar on this picture, is bent around an intermediary object to the observer. So this will produce, this can produce multiple images, arcs or rings, and the light can be magnified or demagnified and sheared and distorted. Yeah, and so we can use this to learn about kind of the matter and the curvature along the line of sight from those objects. So we can learn about the matter density of the lens, but also of space itself. Yeah. And so some real world examples. On the left, we have some lensing systems from the Holy Cow sample. So we have lens quasars around some lens galaxy or elliptical galaxy. And so you can see the host galaxy that the quasars are in is kind of bent into this Einstein ring. And then we have this bright points, which are your quasars. And on the right, we have a cluster doing lensing. And so we see this orange smear, which is a galaxy being lensed. And within that, we've seen a supernova being multiply imaged. And yeah, so I guess takeaways here is that if you assume a background cosmology, so you say the universe is lambda CDM, then you can constrain your lens object. You can find out things about the matter density profile of your lens object. Or you can assume a lens model and a background cosmology, and then you can constrain cosmological parameters. So you can say the lens is this kind of lens, the cosmology is this kind of cosmology, and then you can constrain the parameters associated with those two models. Or finally, you can assume a lens model and then compare the likelihood of different cosmologies to one another, which is kind of the main thrust of this talk. Yeah, but the key takeaway is that the lens model and your choice of cosmology are interdependent. So whatever cosmology you choose will affect the parameters at which your lens model spits out, and vice versa. So I guess, a bit about time delay cosmography. This is the main use of strong gravitational lensing, I'd say. So from the time delay between different images, so if you have a supernova go bang in one image and sometime later it goes bang in another image, or alternatively some fluctuation in a quasar light curve, then you can say that because they've had different times to get to the observer, they've traveled different path lengths, the light rays, and therefore we can infer the expansion of space, your h naught, from that. Now, for supernova, it's very easy because they have very well-defined light curves. But for quasars, it's quite difficult. Cosmogral, the collaboration that measured these things, took years to get time delays for several, maybe like 18 or so quasars. And whilst that is improving, and we are shortening that time, it's still very labor intensive. And this kind of motivates my work. So I'm not using time delays. I'm looking at velocity dispersions as a test statistic based on a distance ratio relation. So I'm looking at the ratio distances between the lens and the source and the observer and the source. These are angular diameter distances. And because I'm looking at a ratio, it's independent of the Hubble constant. And like I said before, I don't require time delays, so I'm not limited to this small sample, but I have a much wider data set of lensing systems to which to analyze. And so what I'm going to do is I'm going to take the measured velocity dispersion from spectroscopy, and I'm going to compare that with the model predictions from different cosmological and lens models combined. And then I will minimize to determine, in a chi-square test, to determine ideal cosmological and lens parameters, and then establish base factors between models. So a bit about the data I use. It's compiled from many different surveys, most from the SDSS galaxies, and it totals 161 systems. Now, these lenses are all elliptical galaxies, so my lens models will hold, which I'll talk about in a second. And we should restrict these systems to isolated systems where there's no interfering mass along the line of sight. So there's no luminous material along the line of sight. Yeah, so there's no multiplane lensing, essentially. And obviously, no system is truly isolated, but, do the best we can. And our largest source of error comes from our velocity dispersion. So we account for, the chances that there is interfering mass or the mistakes in your Einstein radius measurement and things like this. And here we have on the left our distribution of redshifts of the sources. So source on the left, or y-axis, and then lens on the x-axis. So the lens models I use. So I'll be investigating power law models. I'll briefly be discussing the simplest one, the single isothermal sphere, and then the most newest one, the extended power law model. So the single isothermal sphere model is, I think, the simplest power law model you can apply. It's quite commonly used. It has it's an inverse square law for your density, right? So your density tails off with radius over 1/r squared, and it assumes that your dark matter halo is in perfect isothermal equilibrium and perfect spherical symmetry. And then the most newest model I'll be looking at is the extended power law model. So this assumes that, well, it's parameterized given here. So the rho is your total matter density, and it's parameterized by this profile gamma. Nu is your luminous matter density, parameterized by delta, and beta is your stellar orbital anisotropy parameter. And it gives this, ugly relation for distance ratios down here, which is hideous, but whatever. So these are the lens models I use. Power law models are very commonly used in gravitational lensing. Alternatively, people kind of use Navarro-Frank White or plus a luminous component, but this is what I'll be looking at. So when I apply this to the single isothermal sphere, so when I generate velocity dispersions and then fit to measured values, I find that my ideal matter density for an FLRW model is well, 0. There's no matter, but or very, very little anyway. But for timescape, you find a void fraction of around 0.7, and this is in agreement with other values that have been found from different observational tests. So I guess most notably the supernova test, which Zachary Lane and others have done, which we'll be talking about, which I encourage you to go watch. Yeah, so it's in agreement. So it's a good value. For the extended power law, we see more of the same. So we see that the matter density goes to 0, but for timescape, the void fraction is around 0.73, which is pretty much bang on what we'd be looking for. And also our matter density of a lens is around 2, which is what you'd expect, because we expect things to be similar to a single isothermal sphere, but not quite. However, when we look at the actual Bayesian statistics, FLRW models are on the whole preferred, but only slightly. And there's not much real statistical significance for the most nuanced models. So our base factor for the extended power law model is around 0.7, which is not statistically significant. You're looking for a log of a base factor over 1 to mean any real preference. Now, all the lens models, well, all the power law lens models that I looked at predicted unphysical values for the matter density for FLRW models. So you can talk about base factors and you can compare one model to another, but if they both fit badly, then it doesn't really mean much. And ultimately, that's what we have here, is that both timescape and FLRW models aren't fitting well. And so you can compare which model doesn't fit best to the data, but ultimately, if needed, it doesn't really mean much if they're both fitting badly, basically. And that's effect of these lens models, which I'm going to go on to in a sec now. So I was curious about why these values were being returned. Why was the mass density going to 0? So I looked at the distance ratios for each of the lenses and found that regardless of what lens model I picked, I was receiving distance ratios greater than 1, which is physically impossible. It's saying that your source is behind you and your lens is in front of you, or some weird geometry, which doesn't make sense. And a cosmological model is never going to predict that. So it's never going to, any real decent cosmology is never going to tell you that these exist. And so this skews the fitting procedure, was my hypothesis, that these high values were shifting your fit. So I went away and did mock catalogs and simulations. So what I did was I took like fixed values of FV0 and the matter density omega m0, and tried to apply my fitting procedure to this mock catalog I generated to see could I recover the values I put in. And the answer was, well, no. So for FLW models, regardless of what omega m0 I put in, I would always receive a value slightly lower, kind of tending towards that 0. And if I increase the uncertainty larger and larger, it would just go straight to 0. Whereas for timescape, it would always return a void fraction of around 0.73. And so this kind of got me thinking, yeah, this makes sense. It's just returning the values of FE0 and omega m0 that produce the highest distance ratio. It's trying to accommodate for those impossible values that it can never really fit to. Yeah. So I guess in conclusions, but all the lens models I investigated were made bad predictions for distance ratios within lens systems. So it didn't matter what power law model I used, I would always get some systems that were poorly described by these models. And that's a consequence of it being a power law and having it being inverse to my velocity dispersion. So I guess applying one global lens model is not adequate to an entire catalog. There'll always be systems that are poorly described. And we need to have either individual fitting, so applying a specialized lens model to each different lensing system, as you would with, when you're trying to find H0 or these like Holy Cow or TD Cosmo or these other lensing collaborations, or apply more observational data to better constrain each model to each system. So having luminosity density profile, time delays, or magnifications, or image positions, or whatever to better constrain them. And this is really important coming up because there is a large amount of data expected to come in soon. So LSST, Euclid, James Webb, all of these are DES, all of these are predicted to observe far more lensing systems. We're expected to see several orders of magnitude increase in available data. And so if you need to measure time delays for every single one of these, if they're quasars, for example, it might not be feasible, essentially. So analyses that don't require this are I think are very important if they can work. Yeah, so that's just, I guess, what I'm trying to work on. So future work, as I said, would be to model these individually rather than applying this global lens fit to the entire catalog. Looking specifically at observational data, so looking at the lenses that actually do have time lenses, there's not that many, but doing analysis of the ones I have. And I'm also interested in the effect of inclination and deviations from spherical symmetry in lens models on cosmological analysis. So many of these systems have more than two images, and a spherically symmetric model cannot produce those images. So it doesn't really make sense to apply those models to those systems. But yeah, if you have any questions, I'll be more than happy to answer them if you come to the question section. And yeah, thank you for listening, guys.